Hi everyone, great to be here at the Munich Quantum Software Forum. Fantastic turnout, really great to see all the people interested in software across both the Munich Quantum Valley, but also Europe and worldwide. So today I want to talk a bit about escaping Python via Python for optimum performance with PennyLane Catalyst. So it's a bit of a strange talk, but I want to talk a bit about the quantum landscape and how we're predominantly in Python today, the advantages of that and why that happened, and also what we can do to kind of work around the downsides that come from working in Python every single day. So Python has kind of taken the scientific research field by storm. This is two graphs, I think, from Stack Overflow from about 2018, where they were tracking visits to Python parts of the Stack Overflow website, and also seasonal traffic from college and universities. And you can see that overwhelmingly, the traffic to Stack Overflow looking at Python-based parts of the website or questions is led by academia. Of course, there's lots of other people from manufacturing to tech to media working in Python, but a huge amount from academia. And if you look at the traffic from college and universities, we're seeing a huge growth in Python over the last 10 years or so, eclipsing Java, which I think was traditionally a language that was used for teaching undergraduates in universities. So it's been almost phenomenal, this rise of Python in academia and scientific computation. So why is this? A couple of reasons. I think the really big one is that Python has allowed scientists to be productive faster. It's a language that is relatively intuitive, I think, for people who have been in the sciences working in undergraduate courses, haven't necessarily had a programming background, but they need to level up and get that programming experience to be able to do productive science and research. So it's allowed people to be productive much faster than I think traditional languages. Having said that, it's slow. It's an interpreted language. There's a bit of a trade-off between how productive it allows you to be quickly, but then also the performance potential of it. So another reason why is that it's been able to act as a glue language between more performant languages. So people have been able to use Python and very easily access code written in languages like C or Fortran or Rust, for example, and still eke out performance where they need it. But maybe the two biggest reasons. The one is the rise of GitHub and the rise of the scientific ecosystem. The ability for us over the last 10, 20 years to be able to pull together code that's made us more productive in our work and easily share this on the internet for others to use, to depend upon, to extend, to generalize, has built this really amazing wealth of ecosystem of scientific research code in Python that is causing almost a chain reaction, allowing people to become even more productive faster because there's so much they can build on top of. And I don't want to skip over too much the rise of GitHub, but open source is really a new concept in a sense, in that the ability to write code and very easily share this with the wider community in a way that people can build on top of and can copy and extend is relatively new. So here's a plot of the total number of open source repos, I believe, on available online from 1993 to 2017. So you can see that the internet and GitHub and tools like GitLab have really made a difference there across academia when it comes to being able to share code and packages. So with that said, I want to talk about PennyLane, which is the quantum software framework that we're developing at Xanadu. So our aim with PennyLane is essentially build a quantum software package that helps researchers do research faster. We want to make sure that it has the features that allows you to do the work that you need to be able to do to publish that important paper or extend interesting and new novel results. So really, really geared towards enabling research in the field because it's important to build these algorithms and work out what this killer application of quantum computing is going to be when we have the hardware available. So a very brief overview for those who are not familiar. PennyLane is a Python library for differentiable programming of quantum computers. It's Python-based, primarily because a lot of researchers are working in Python. It has a really great ecosystem. It allows for rapid prototyping and also exploration. So it integrates with a lot of existing Python frameworks that we have, like NumPy, SciPy, Pandas, for example, that become kind of the basis of a lot of work that's happening in quantum software and quantum computing research. So a very brief overview here on the left. Very simple hello world-esque example. You can create a Q node, which is a function that just specifies quantum operations that can be executed on a quantum hardware or a quantum simulator. You can specify measurement expectations, statistics, probabilities that you want as output for your device. So there's a bit of classical processing that's implicit here just to make it a bit easier as well. And then you can easily mix and match this with Python libraries like NumPy, SciPy, for example, to compute cost functions, to compute gradients, and to train various aspects of your quantum model. So it has a pretty much a functional sort of interface defined around having these quantum functions. We realize it's important as well to be able to execute on simulators, prototype, and then scale up, try on different hardware devices, especially in the NISQ era where we have lots of different hardware modalities that have different strengths and weaknesses, and we might want to use them in different places. Or perhaps use multiple hardware modalities in one workflow, for example. And then the final thing is everything differentiable. So our goal with PennyLane is to make sure that every aspect of the code that you're writing in your hybrid quantum algorithm is differentiable so that you have the ability to train it. ML tooling has been incredibly valuable over the last 10, 15 years. Tools like TensorFlow, tools like PyTorch, tools like JAX from Google. And these have kind of changed how a lot of scientists, especially in computer science and machine learning, think about programming. You can now have this paradigm of differentiable programming where you can construct a model and then arbitrarily train any aspect of this model, including the structure of this model. You can have control flow, you can have if statements, you can have for loops. And this all remains differentiable, and you can train not just the parameters of your model, but actually what the model looks like. So what we're trying to do with PennyLane is include quantum into this paradigm so that you can arbitrarily mix and match various quantum executions, quantum functions, classical processing, and then train this. Whether this is for application-specific approach, quantum chemistry applications, or you have a very specific thing that you want to characterize, for example, on a quantum simulator. You're not quite sure how to get there, you could derive a cost function that allows you to try and train to get to that characteristic that you want. So we have a very strong focus on research and enabling applications. I've got a couple of examples here from the PennyLane website. These are just two of the 160, I believe now, research demos that we have on the website, where the aim is to kind of highlight what is the latest research coming out of the archive, and can we write it up in a way that is very easy to understand and also reproduce with code. So we have examples here of topics that might be interesting and are kind of in the vogue at the moment in the quantum space. So things like dynamical Lie algebras, and also demonstrations showing how we can take advantage of this integration with machine learning to do things like differentiable pulse programming, for example. So mix and match gates, but also pulses in your model, and then train those pulses to achieve some sort of outcome. It's also very easy to interconnect PennyLane with those machine learning frameworks I mentioned, like JAX, TensorFlow, and Torch. So we have a lot of demos reproducing a lot of really nice research coming out of the archive recently. So the generative quantum eigensolver was a really nice paper by University of Toronto and NVIDIA, where they showed that you can actually combine elements of LLMs to almost tokenize and treat the quantum circuit ansatz that you're building as a large language model. So that's our goal with PennyLane and what we've been building so far. I want to discuss a bit the sort of general paradigm of quantum software that we see in the industry today. So PennyLane is the one that we're building. This is a bit of a generalization, but primarily a lot of the software tools we see are Python-based. And this is for good reason, as I mentioned. It's very popular, it allows us to be productive much faster. We're still primarily programming at the level of quantum circuits. So a lot of the major quantum software frameworks, you're specifying qubits, you're specifying gates, and you're directly applying this to your circuit. And then if you're executing on hardware, this involves a couple of things. First, you're likely optimizing the circuit. when you go to execute the circuit. So you're executing the circuit, it's going down some sort of pipeline. You typically have the parameters of your circuit at this point. And so all this is used to do the compilation of the circuit for the hardware and to minimize the circuit depth. At this point, after compilation, you've serialized just the quantum component of the circuit. So you've extracted just the gates and the qubits they're applied to from the snippet on the right. And you now just have a long list of gates. This could potentially be very large, especially if you're working with fault-tolerant quantum algorithms. And now you're submitting the circuit for execution, perhaps via a simulator, perhaps via a cloud REST API for a quantum platform, for example. So a brief overview of what this looks like in PennyLane. You have a cost function here. You notice that the circuit I have has a bit of structure, so I'm using for loops, I'm using if statements, just because it makes it a bit easier for me as a researcher to code up the structure of the algorithm that I have intended. So I've got this circuit here. I've now also got this cost function below where I'm doing some classical processing. And I might want to execute and find the gradient of the circuit. So I generate some data, I generate some weights, and I ask PennyLane to compute the gradient, and I get the result here. So this is doing a hybrid quantum classical computation. So under the hood, what's happening? We're computing, we're basically unrolling the structure of the circuit. We're going through with the Python interpreter, we're capturing all the gates that have been placed in the circuit through that for loop, through that if statement, which we're able to evaluate because we have all the runtime parameters. And we end up with this list of gates that is kind of separated out of the quantum from all the classical processing plus the classical structure. But this isn't it. So at this point, we now actually have to do the compilation. So we have to pick a quantum hardware device or a simulator, for example. If it's a simulator, it's a bit easier. Typically, the gates we have will execute. If it's a hardware device, then we have to match the native gate set. We have to match the topology of the device. And we end up with something potentially quite a lot larger than that initial list of gates we had. So that's what quantum software is doing today. We've got sort of that very rough, and this is a generalization. There's very interesting projects outside of this as well, outside of Python, outside of this quantum circuit. But in general, this is what we see with the major frameworks. And it makes sense. It's an intuitive UI, it's easy to debug, it's a rich standard library. But I think it's a problem that we see, and we see this in research as well, right? Where you start prototyping in a language that allows you to move fast, and you're hacking together. You want to verify that your algorithm's working, and this is perfect. But as soon as your idea matures and scales, and you want to start pushing the limits of what you can do, you will care about these drawbacks of Python, where it's not necessarily that fast, where it's not necessarily that performant and able to target the devices you want. So the question is, can we do better than this? Quantum workflows are inherently hybrid. You saw from that example before that I was mixing quantum and classical, but this is essentially the case for almost all algorithms. Even the classical textbook algorithm we think of for quantum computation, there's still classical processing involved there as well. Everything's also happening in runtime at Python. And Python's an interpreted language. This won't necessarily be as performant as you want. And compilation is also a difficult problem. We might not think about it so much in the NISC era when we're not really focusing on deep circuits, but as we're going down to the path to fault tolerance, we're going to be ending up with potentially very, very deep circuits at the millions or 10 millions of gates deep. So it's a problem that we need to face head on. How do we build the infrastructure that is going to support these types of algorithms down the line? So even though quantum workflows are inherently hybrid, we're also splitting the computation. We're doing the classical part locally, potentially in Python. We're then serializing out the quantum and sending it through potentially a server-side queuing system. So there are abstractions which are very heavily separating where the quantum code is being executed and where the classical code is being executed. It's also not allowing us to really explore these types of adaptive algorithms that Bettina was talking about previously in her talk from NVIDIA. So you have algorithms that we want to explore where you have potentially unbounded while loops where you're doing measure until success routines. You're measuring qubits and you're just repeating this while loop until you get the measurement syndrome that you want to measure. These are patterns that are super important both in error correction research, but also in exploration of how we can use adaptive algorithms to improve what we are doing in algorithm design. So these types of patterns here, we want to enable those, and we can't always separate out the classical and quantum like we've done. So at Xanadu, we were thinking, can we take inspiration from other packages? This is a problem that other domains have faced. Machine learning for sure. Machine learning tooling is very much embedded in Python, but they need the ability to execute in GPUs. They need the ability to execute and compile outside of Python. So you can still rapidly prototype, but you can execute much faster and really scale up. So Number and JAX are two really good examples from the Python ecosystem that allow this idea of just-in-time compilation, where you can code in Python, but it's not compiled and executed in Python. So that's our main goals. We want to keep the quantum and classical together. We want to compile that full hybrid workflow and keep the execution of the quantum and classical parts of your workflow very close together. And there's other questions we have as well. Can we optimize the program ahead of time when we don't even have these potential runtime parameters yet? How much can we optimize in that compilation step before we have all of the information? And again, echoing, I think, Bettina's talk earlier, can we utilize existing classical compilation infrastructure with decades of development as opposed from doing what we've tended to do in the quantum ecosystem in the past, which is start by building something that is quantum and adding classical into that? But can we utilize what's already out there? So for the past, I would say, year and a half, I think, as Xanadu, we've been working on this idea of Catalyst, which is a compiler for Python that enables quantum just-in-time compilation. So you can continue to work in PennyLane and write your code in Python using a mix of different Python-compatible scientific ecosystem libraries. But we can now use this to capture your hybrid program, so all the classical, all the quantum, and compile this for execution on CPUs, GPUs, and QPUs. So here's a brief example. I've got the PennyLane code on the left, and this is essentially standard PennyLane code. The only difference here is I now have this QJIT decorator. And what this QJIT decorator is specifying is that this Python code, which would execute fine without this QJIT decorator, is now going to be captured and compiled before we know the runtime parameters. So we've got to do the compilation ahead of time with, and compile this down to a native binary. Subsequent executions of this code will actually call optimized machine binary instead of executing in Python. So there's a very brief example here on the right. I'm just executing the circuit. You can see that it has a for loop. So I'm going to call it with 10,000 iterations of this loop, and executes in about 700 milliseconds or so. What I can then do is I can take this circuit and apply this QJIT decorator, execute it again with the same number of loops, get the same result, but almost a factor, 2 orders of magnitude faster in execution. And this is primarily because we're escaping Python. This is a very small, contrived toy model. It's not doing anything that computationally intensive. This overhead is just because we're now no longer in Python land for this execution. But you can go bigger than this. In that example there, I was just in time compiling a single circuit execution with structure, so for loops and if statements. But you can also use this to compile an entire workflow. So in the example here, I'm doing an optimization. And in a hybrid optimization, you might have a for loop around quantum circuit execution. And this quantum circuit, you could be executing with different parameters every time you iterate this for loop. So you can actually quantum just-in-time the optimization itself. So you're compiling down a binary that itself contains a for loop that is calling a quantum circuit. And this is a regime where you see an even bigger advantage to escaping Python, for example, because you now have a for loop that is executing from this binary, and you're not having to call back into Python, execute a potentially much slower Python for loop every time you want to do this grid search or optimization of your circuit. So if you really think deeply about your hybrid circuit and you figure out how can I push this quantum just-in-time compilation further, you have a really nice playground where you can prototype purely in Python with small-scale problems, verify that it's working, and then use quantum just-in-time compilation to start scaling up the performance of your problem. Another really important thing I want to mention as well is structure of quantum programs and control flow. When we're thinking about adaptive programs, and if we want to code them up in Python, we'll typically have things like for loops and if statements. And we have mid-circuit measurements. We want to be able to use them, either for error correction research or to explore how we can do better algorithm development. So we need Python code that represents our research workflows to be able to have their for loops and if statements work with things like mid-circuit measurements. So there's a brief example here where I have a circuit that is preparing a state and measuring some of the qubits. So I get measurements M0 and M1, they're now classical values. And I essentially have a for loop here where I'm just repeating this prepare and measure subroutine until the two measurements I've measured of those qubits satisfy some contrived condition, for example. This is something that wouldn't work in standard PennyLane, but if we use the QJIT decorator, we can capture this control flow, compile this down to a binary, and actually execute these control statements at runtime. So it enables this much more adaptive style of programming in Python, but something that will be supported on both simulators and hardware devices that support adaptive circuits and mid-circuit measurements. There's another reason why this is super important as we start scaling up our programs. So a lot of the algorithms that we're looking at, a lot of the ones coming down on the archive, are increasingly having dynamic quantum circuits, but at the same time, they have structure. Almost all the algorithms we're exploring, the ones that we feel will have meaningful applications on quantum computers, have a structure that we shouldn't ignore. And it's relatively straightforward even to represent why we shouldn't ignore this structure. So here I've got a very brief example where I've got 2 Hadamard gates, 2 RX gates, and it's just within a for loop. So I've got a for loop over these 4 gates. They're being repeated n times just to scale up the size of the circuit. If we use PennyLane without the ability to capture the structure and then we compile this down, so we're potentially compiling this to reduce the circuit depth, we find that as the size of our for loop increases, of course the size of our program will increase because we just have a very long list of quantum gates. So this is not scalable. Trying to compile this increasingly larger and larger list of quantum gates is just something that's not going to work in practice. But if we just capture this for loop and we build our compilation passes so that they don't unroll this for loop, that they compile everything within the for loop, and they also look at the for loop boundaries so they know, okay, if I have a Hadamard gate at the end of one for loop and iteration, and another Hadamard at the beginning of the for loop iteration, I can cancel this out across iterations. So if you don't unroll that for loop and you do compilation smartly with the structure preserved, you essentially get constant overhead for compilation because the size of your program is not increasing as the representation size of your program is not increasing as your workflow increases. And you can see this with common algorithms. So Shor's algorithm is a really good example of an algorithm with structure. And this is just a quick comparison of comparing the compilation time between Casless with its quantum just-in-time compilation capturing the structure of the program and compiling with the structure preserved versus PennyLane without this just-in-time compilation and we're not capturing the structure. And you can see that in general, as the size of the number that you're factoring with Shor's increases, that compilation overhead is also going to increase if we're not preserving that structure. But preserving that structure allows us to have almost constant overhead for compilation. And maybe just a final plot to demonstrate that escaping Python speedup. So this is an example of VQE chosen just because it's a very general representation of an algorithm where you have an optimization loop over circuit executions. But you could generalize it to any workflow of that form. The dashed lines are compiling and executing in Python, and the solid lines at the bottom, that's using Catalyst and quantum just-in-time compilation. So here it's really representing that speed up you're getting just because we're not executing this in Python anymore when you're using just-in-time compilation. So it's really essentially removing that Python overhead from the execution of the workflow. And similar to the demos I was showing earlier in terms of what PennyLane supports from the research side, I encourage you to also check out the website because we have a lot of demos as well on quantum just-in-time compilation and why it's so useful and where you might want to use it to enable these adaptive style algorithms, and also advantages in compiling structured programs and minimizing runtime by avoiding Python. I'll briefly talk under the hood about what's happening when you're using Catalyst and quantum just-in-time compilation. So this is a brief overview of kind of the 3 stages that we have in the system. So the very first stage, we have the Python front end, and this is using a combination of Python and JAX, the machine learning library from Google, to capture both quantum and classical processing. So JAX provides a NumPy compatible library with all the standard NumPy functions. Combining this with PennyLane's quantum operations, we're able to capture almost all combinations of quantum and classical workflows. We then, after we've captured this program in Python, we then lower this down to MLIR. MLIR is a great framework for representing more high-level intermediate representations. You can mix and match different dialects. So we have a quantum dialect, a gradients dialect, dialects for representing control flow, for example. So it's a really nice avenue or place for doing this more high-level compilation. So at this point, we're compiling and doing classical and quantum optimizations. It's then lowered down to LLVM QIR as the low-level representation of the program. And the final stage is just a runtime that's able to interpret the QIR instructions and dispatch or simulate them on dispatch them to hardware or simulate them. We designed it with these 3 components somewhat deliberately because we want to make sure that what we're building is modular. It's a case where we realize that these different components of the stack, so the front end, the compiler, and the runtime, may have different advantages to different people, different groups, different researchers. And by keeping them a bit separate, we're able to allow people to use only one component or only 2 of those components if they want. So this is an example of from the CRISP framework from Fraunhofer. So it's a really nice framework for higher level abstraction quantum programming, for example. In their case, they already have a Python front end that they're interested in utilizing compilation and runtime. So they've added a quantum just-in-time decorator. I think still in development at the moment, but should be released relatively shortly. And the really nice thing about this is it's using the CRISP front end. You can code up with the higher level abstractions and operations, but when you use the quantum just-in-time compiler decorator, it then captures this program and lowers it down to the Catalyst compiler for compilation to a machine binary. So deliberately keeping those 3 components separate enables us to work with different groups. If, for instance, someone's only interested in the front end we've built or only interested in the compiler, we can explore different integrations across the quantum ecosystem to find benefits for multiple people. So we've done a lot of work over the last 1.5 years kind of building up this infrastructure for capturing hybrid programs from Python and compiling it. But there's very much still a lot of work that we have to do. So there's a lot of work in terms of figuring out how this integrates with circuit compilation. How much compilation can we actually do when we don't have all the information about the runtime parameters of the circuit? How much can we do in advance? How much do we want to do in advance? How do we deal with the fact that there'll likely be multiple compilation stages, some at runtime, some at compile time? How do we map all these really exciting compilation passes and theory coming out of the literature to practical applications where we want to write compiler passes that don't unroll control flow? And how do we, again, map these to dynamic and adaptive circuits that have mid-circuit measurements? Error correction is a really good question as well. I liked in the previous talk from Bettina, where there was a bit more thought in terms of where error correction sits in the stack, because for us it's very much an open problem. It could fit in multiple areas with potential trade-offs in different places. And again, what does the infrastructure for this compilation of structured adaptive programs look like with hardware? So I think a common theme is that we're seeing a lot of quantum computing companies in the space and startups and research groups exploring LLVM and classical compilation infrastructures and adding quantum support to those. We see ourselves at the moment in that it's very much an R&D project. There's still a lot we don't know. It's still very much connected to the research. The paths we take now will define those software paradigms in the future, but we still don't have all the answers. So I've got a bit of an open call here to everyone to get involved, contribute, and help build that next generation of quantum software beyond that long list of unrolled quantum gates. Catalyst is open source. It's available on GitHub with Apache 2.0 license, so definitely feel free to check it out, have a look, go through our documentation and our tutorials. As I've mentioned a couple of our demonstrations as well throughout the talk, so definitely go and have a look. This slide's a bit out of date because I think we now have about 160 plus demos available. And one final thing, which is the Unitary Fund survey for open source quantum software closes October 31st, 2024. This is a fantastic resource for the broader quantum community to share their feedback and indicate what they need and what quantum software they're using. So definitely, if you haven't already, it only takes a couple of minutes. Feel free to head to the website here and fill in the survey before it closes. Thank you, everyone.